am your lecturer for this semester for engineering materials. So for a change, we will be having an online class where I'll be conducting all the classes virtually, including practical, tutorial, and also lecture. So I can't see your faces, but I'm hoping that there are some ex-students of mine in this class as well. All right. Just hold on for a moment. Okay, guys. Now, for today's lesson is going to be on the introduction of material science. Engineering materials, the introduction of it. And also, I will be starting our first lecture, which is imperfections in solids. All right, this is going to be very different from what I've taught before because we'll be having an face-to-face classes, but here is all cluttered into online. So I want you to focus because it's going to be very intense. Okay, it's going to be very intense, packed with knowledge, and try not to miss my words. All right. I hope that you can enjoy the presentation today. If you have any question, you can always write in the chat box. All right. Now, can you hear me? Can someone just type yes? Okay, that's great. Thank you. Thank you very much. All right. All right. I'm getting a lot of yes. Thanks. Okay. Now, the introduction. Now, this is 3 hours, 3 credit hours subject targeted for ME, ME and MH, and also, yeah, ME and MH. All right. Okay. Method of delivery is lecture, tutorial, and practical. All right. The course objective of engineering materials is to provide engineers with a framework in which the structural, mechanical properties, interrelation of engineering materials can be rationalized in order to predict performance at the design, manufacture, and in-service stages. So, guys, for engineering materials, I'll be teaching you the fundamentals of material, the manufacturing parts of material, manufacturing subjects of material, and also a little bit on the properties of material. Okay, there are 3 basic building blocks of engineering materials. Okay, the first one is the fundamentals of material, which I'm going to start today under lecture 1, imperfection solid. The second part will be basic introduction on the properties of material. And the third phase would be manufacturing of material. All right, this covers the whole engineering material course for this semester. All right, so if you could master these 3 key points, then it's easy for you to achieve good results on this subject. All right. Okay, for course learning outcome, you can just go through these. You can just go through these course learning outcomes. There are 5 course learning outcomes. The first one is correlate the structure of a material with its behavior and performance at different temperature related to properties of material. The second course learning outcomes is to evaluate the methods of assessing the material's mechanical behavior, which is covered in the fundamentals of engineering materials, the first part of this subject. The third one is outline the important criteria on material processing application, which is the third part of this subject, which is the manufacturing part. The fourth course learning outcome is evaluate material properties for suitability in engineering related applications and better service of performance material properties. And the fifth course learning outcome is conduct experiment with data analysis and interpretation. All right, for the fifth one, we will be having, last time we will be having our lab session in the lab, but now since everything is becoming virtual, so the practical lessons will be conducted here online. Okay, I'm in the midst of creating video, practical video. I went to Utah and took some videos for you guys, and I'm editing now. So next week I'll be seeing the first batch of the first group for the practical session, and we'll discuss further on that. Right, everything is online here in Microsoft Teams. Okay. All right. Now, lecture, tutorial, practical, everything is covered by me. So it is very clear. Anything you can always email me, right? Okay, hold on a second. There's one student asking something. So what if my laptop cannot support the software for simulation? What simulation is that? Can you type it out? Or you can on the mic if you want to talk to me. No. There is no simulation for this practical session, right? I'll be showing you the video, explain to you what is this experiment all about, and then you interpret it in a report. That's all. No simulation. Don't worry. Do I answer your question? Nur Harpinda. Okay, all right. Okay, guys. So we shall continue. This is my office, level 3, GE27. Unfortunately, now I'm at my home in Klang. So you can email me if you want anything or any clarification, or during the class you can always chat. All right. Okay, now the course outlines. We have taught 4 topics. First topic is secondary method for processing materials, which is the fundamental. Topic 2, structural steel, cast iron, and ferrous alloy, which is the properties of material. The third one is the manufacturing process. Same goes to topic 4, which is the service performance. All right. And this is the main reference that I'll be looking at into creating the lecture content. And frankly, this lecture content I've been here for so many years, so I'm just using the same content again and again. And I'm sure some of you have taken this subject before. All right. Okay, now this is the important one. Students, please take note of this. For lab, the overall percentage mark allocation is 10%. Quiz is 10%. Test is 20%. Assignment is 20% as well. And the final assessment is 40%. Okay, now I will be uploading the teaching plan by this week, so you can look into more detail. When is the test, when is the assignment, and so on. Okay, I haven't uploaded the Webble, but I'll be uploading it very soon by this week. All right, for practical, you have 2 topics. The first topic is annealing. Two practical actually, annealing, and the second practical is fatigue test. So I've walked into Utah and recorded some videos so that you can understand more in depth when we'll be having this session next week. Okay, practical starts in week 2. All right, laboratory person in charge for Rosmawati and Mr. Saiful. Very sure that you know them. Very dedicated lab officers. And tutorial starts in week 2, next week onwards. All right. So this is the introduction for engineering materials. All right. Do you have any question? Any questions? Okay, I assume that there is no question. Thank you very much. Okay, now let's go to lecture 1. All right, I've uploaded lecture 1 in Webble. You can have a look on Webble. Now, lecture 1 is deals with the fundamentals of imperfections in solid. All right. So when you look at the word imperfection, I'm going to cover the whole 33 slides today talking about imperfections in solid. You have perfect solids, you have imperfect solids. Perfect solid only exists in theory. Okay, write it down, or you can highlight this. Perfect solids only what they call that exhibits in theory. All the materials in this world are imperfect solids. There can be many reasons for it. All right, some of them are artificial, some of them are naturally occurring. Okay, hold on. There's one question asked me a student. Are we going to Utah for practical? Low Kai Kin? No. You don't need to come to Utah for practical. Everything will be conducted online. Okay. Let me write it down. All practical. Okay. All right. All right. There's another student asking me a question. How was the attendance taken? All right. For the attendance, I will create a Google form later. Not Google form, a Microsoft Team form later. In a while. Just in a while. All right. Hang on. Okay. Now, imperfections in solids. Now, this is the outline for today's lecture. There are lots of types of imperfection of solids, but I'll be covering only some of it. All right. The first one is point defects. By the word point defect, you should be able to interpret this point. All the defects are in terms of point. And then you have impurities in solid. For example, alloys. Alloys are impurities. Then you have dislocation. Dislocation is another imperfection in solid. Then you have interfacial defects. And then the last subtopic of this lecture is specification of composition, which is nothing to do with imperfection in solids. It's just a specification, just a what they call that a calculation. All right. I'm giving you a formula. You calculate what is the weight percentage or atomic weight percentage of different types of material in it. All right. Okay. Now, imperfection in solid, it branched out into 1, 2, 3, 4, and 5 types, which is point defects, dislocation. Okay, the first one is point defect. I'll be discussing about point defects in a while. And then you have dislocations, linear defects. Then you have interfacial defects. Then you have bulk or volume defects. And then atomic vibrations. All right. Now, let's talk about the first one, which is point defects. Right. Now, the definition of point defects. Point defects means that you can highlight this: an atom missing or is in an irregular position in the lattice structure. So you know lattice structure, you have lots of lattice structure, right? HCP, BCC, and so on. So an atom missing or in irregular position in lattice structure. So that is point defects. Okay, it can be either a missing vacancies. Okay, you don't have it is a missing atom in a lattice structure. It can be self-interstitial atom, a small unknown atom which is inside the lattice structure. It can be interstitial impurity atom, much more smaller atoms, or it can be substitutional atoms. All right. So just a quick recap. I'm talking about point defects, and under point defects, the definition of point defects is missing atoms or in a regular position in the lattice structure. And there are few types of point defects, which is vacancies, self-interstitial atom, interstitial impurity atoms, and substitutional atoms. All right, now let's talk about vacancy. Vacancy is an empty space, okay, vacant, all right, vacant electric site where atom should be, but it is missing. So if it is missing, it means there's some impurities and there's some imperfection in solids, right? Vacancy is formed due to a missing atom. Highlight this. Um, and then vacancy is formed during crystallization, solidification, or mobility of atoms. All right. Vacancy is formed during crystallization of an atom, solidification of an atom, or mobility of an atom during crystallization, solidification, and mobility. Please highlight these. It is also caused due to the plastic deformation or rapid cooling or particle bombardment. Plastic deformation due to stress, rapid cooling due to thermal stress, or particle bombardment, change of chemical properties. All right, so let's say this is your structure, all right, atom arrangement, and then suddenly there is a missing atom in it. So that is what we call vacancy, under point, defect, imperfection. All right. Okay. All right. There are a few questions here. Okay, now guys, give me about 2 minutes. I'll create the Microsoft form and then you can start putting your attendance in. Okay, I have created the form. So all of you, please select yes if you attend the class. Okay, now we shall continue with the lecture. Oh, I was at vacancy. So this is the definition for vacancy, where there is a missing atom. Just a quick recap, there's a missing atom in the structure of any atom. So when there's a missing atom, so you will have a distortion in planes. Okay, you will have a distortion in planes where the atom above or adjacent to it might distort, okay, might slip between the missing space. So that will create an imperfection in solid. Right? Now, there's a small formula for it. NV is the number of vacancies per meter cube. For you to find the number of vacancies per meter cube, this is the formula that you need to use. Please take note of this. All right? The description is state here. NV, number of vacancies per meter cube. N is the total number of atomic sites, usually per meter cube. And here, Qn is the energy required for the formation of a vacancy. J mole or EV per atom depends on the value. You need to use the correct Boltzmann constant, right? If it is in J mole, you need to use 1.38 times 10 to the power of negative 23. If it is in EV per atom, you need to use 8.62 times 10 to the power of negative 5 EV per atom dot K, the Boltzmann constant. Please take note of this. And also, a lot of students make mistakes by taking T in degrees Celsius. Actually, it must be in kelvins. Right? Please take note of this. I don't want you to make a mistake on this silly carelessness. All right? It is quite hard for you to digest because usually all the formulas are in Kelvin. Right? A lot of students make mistakes. They key in the formula in Celsius, degrees Celsius. All right, now after vacancy you have self-interstitial atoms here. All right, now a self-interstitial atom, you have two types, which is interstitial impurity and also self-interstitial. Both are actually the same. One is a smaller size, another one is the same atom. All right. It is opposite to the vacancy, where a self-interstitial atom is an extra atom that has crowded its way into an interstitial site, a small void space that under ordinary circumstances is not occupied. Okay, if you have any voids, usually in material, if you have any voids, there is some foreign element, okay, for interstitial impurities, or the same material, self-interstitial, which doesn't have any pair. So it just hang around there and it distorts the plane in this direction. Right? Bear in mind that self-interstitial is not natural. It needs to induce artificially, right, by particle bombardment or something. Right? Atom in a crystal sometimes occupies interstitial site. This does not occur naturally. Right? Can be induced by radiation. These defects cause structural distortion. All right, please take note. Point defects, we are at the self-interstitial atoms. Now, impurities in solid. Now, after point defects, we are now in impurities in solid. All right. Any questions in point of defects? Okay, if there's no questions, let's talk about impurities in solid. After that, I'll give you a break. Then we'll continue with dislocation and so on. All right, now impurities in solids. Now, impurities in solids means that any alloys, okay, you have your phone, right? I'm very sure that you have your phone right now, and the phone casing is actually impurities in solids. It's an alloy. Addition of different materials to become one. It might be targeted to improve the mechanical properties or the thermal properties or any physical properties of the material, right? This is where my research is all about, okay? You have solid solution. Solute atoms are added host material, matrix material, a solvent or host atom. The crystal structure is maintained and no new structures are formed. Example, alloy. Okay, you add something in the host material. That something can be anything, but there is rules for it you need to follow, right? So the impurities is substitutional and also interstitial. Two types. Please highlight this: substitutional or interstitial. All right, for substitutional impurity atoms, atoms of a different type than a bulk atom which has replaced one of the bulk atom in the lattice. I'm repeating it. Substitutional impurity atom, atoms of a different type than the bulk atom. Okay, atoms of a different type than a bulk atom which has replaced one of the bulk atom in the lattice. So it replaces one of the bulk material in the lattice. Whereas for interstitial impurity, an atom of a different type than a bulk atom, it is much smaller than bulk atom. Highlight this, and then it fills the void or interstices among the atom. It doesn't replace. Okay, substitutional impurities replace the atom. Interstitial impurities fills the void. Okay, there's a difference for it. Please take note of it. All right, guys. The attendance, I have only 47 respondents, but here we have 50 students, including me, 50. So missing 2. Please check who haven't key in the attendance. Please key in the attendance. If you have friends that haven't keyed the attendance, just inform them if they are beside you, or if you know that someone haven't signed the attendance. Okay. All right. Okay, I shall continue now. Impurities in solid. Now, I did mention to you there's some rules, right, for you to add different types of material. Now, conditions for substitutional solid solution, we call it Hammurabi rule. Okay, there are 4 conditions, which is atomic size factor, highlight this, crystal structure, electronegativity, and also valence. Okay, 4 rules, which is atomic size factor, crystal structure, electronegativity, and also valence. Now, for atomic size factor, the size between 2 different types of material must be less than 15%. Highlight this. Okay, you can read this. For atomic size factor, the size must be 15%. For crystal structure, for appreciable solid solubility, the crystal structure for metals of both atoms must be same. The crystal structure must be same. If it is BCC, the impurities must be BCC as well. If it is HCP, the impurities must be HCP as well. Okay. The first rule is the atomic size must be 15% or less. The second, the crystal structure must be same. If it is above 50%, what will happen? Otherwise, the solute atoms will create substantial lattice distortion and a new phase will form. So it is different phase. It means that you have 2 different, what they call that, planes, which eventually deteriorate the mechanical properties or any properties that you intended to increase. Okay. Next, the electronegativity. The rules are the more electropositive one element and the more electronegative the other, the greater the likelihood that they will form an intermetallic compound instead of substitutional solid solution. So you need to have less electropositive and less electronegative. It means that the distance between electronegativity must be reduced. Then you can create the substitutional solid solution, which is an alloy. Another rules is valence. Other factors being equal, a metal will have more tendency to dissolve another metal of higher valence than the one of a lower valence. For example, in aluminium nickel alloy. Nickel, which has a lower valence, can dissolve 5% of aluminium. Okay, nickel, which has a lower valence, can dissolve 5% of aluminium. But in other hand, aluminium, which has a higher valence, dissolves only 0.04 percentage of nickel. So you need to have the host must have a lower valence. The host must have a lower valence. Please take note of these. So the rules for substitutional solid, according to Hami rotary rule, the first one is atomic size factor must be 15% or less. The second one is crystal structure must be same crystal structure. The electronegativity must be small, and the valence must have lower valence for the host. Okay, here you can look at these, and would you predict more aluminum or lead to dissolve in copper? This is copper, atomic radius, electronegativity and valence, and aluminum is here, copper is here. So which would you choose? First look at the atomic radius. Make sure the size is less than 15%. If the size is less than 15%, then we clearly see that aluminum is the correct choice, is the right choice. Okay. All right, guys. I will give you a break for 10 minutes. All right. 10 minutes means I'll be seeing you at 2:45. All right. Or you want me to continue? Anyone? You can chat here. You want me to continue, or you want me to give you a break? Okay, okay, enough. All right. I'll give you someone need a break. All right. Never mind. It's okay. So I'll give you a break for 10 minutes. Okay. Only 10 minutes. Be here by 2:40. 8 minutes. 8 minutes break. All right. Be here by 2:40. Okay then. Okay, students, it's 2:40 now, so I'll be continue with the lecture today. Can you hear me? Can you hear me, guys? All right, all right, all right. Someone is having a Kit Kat. So much for a virtual class, huh? I hope that you can have your good times at home. You can eat, you can do whatever you want, no problem. But just that try to concentrate, right? If you have any question, just ask me. Chua Yun Chin have shown Kit Kat, and I'm hungry now. All right, guys. Where am I? Okay, now. You can see the slide now, right? Can you view the slide now? Okay, all right, good. Thanks, Theo. Okay, now let's talk about dislocation. All right, before we start on dislocation, just want to have a quick recap. Today is about imperfection in solids, and I've covered point of defects, impurities in solids. In point of defects, you have vacancies, self-interstitial atoms, interstitial impurity atoms, and substitutional atoms. And then impurities in solid solution, you have substitutional and interstitial as well. And then the rules that governs impurities in solids in terms of solid solution is according to Hammurabi rules, we have four, which is atomic size factor, crystal structure, electronegativity, and also valence. Right, now let's talk about dislocation. Dislocation is another imperfections in solid. All right, dislocations, when I tell you about dislocation, you can imagine about a line, a continuous line. Okay, dislocations. Okay, so dislocations are line defects. Highlight this. It is a linear defect around which some of the atoms are misaligned. Lattice distortion are centered around the line. Okay, lattice distortions are centered around the line. So everything is misaligned. Right? The keyword are line defects. It is the dislocations is the slip between crystal plane results when dislocation moves. Usually this happens when there is an external stress imposed to the material. Highlight this. Usually this occurs when there is an external stress imposed to the structure. Alright, here. Formed during solidification, permanent deformation, this is the external stress, this is the main culprit. Atomic mismatch in solid solution as well. Right, schematic of zinc, hexagonal, close packed. Before deformation is this, and after tensile strength, after tensile elongation is this. Okay, slip steps. All right. So now there are few types of line defects, which is H dislocation, screw dislocation, and mixed dislocation. All right. For H dislocation, it is created by insertion of extra half planes of an atom in a lattice. For example, imagine this is your lattice structure. Okay, 1, 2, 3, 4, 5. So that is perfect, right? Suddenly, you insert a new lattice lines or planes. Okay, so what happened? It tends to bulge this region. So this is your H dislocation line, and this is the half plane that you have inserted. Okay. The dislocation is called line defect because the locus of the defective points are produced in the lattice by the dislocation lie along the line here. Right? Burgers vector shows displacement of atom. Okay, displacement of atoms. Right? If you look at the vector, displacement of atoms, slips or measure of lattice distortion in terms of magnitude and direction. right? So this is the edge dislocation, and that is the line which is going through in. Now next you have screw dislocation. Screw dislocation is created due to the shear stress applied on the region of a perfectly crystal separating by a cutting plane. So for example, this is the surface. When you apply a shear stress on it, okay, this is your cutting plane. When you apply a shear stress along this line, all right, one move here and another move in this direction, so it shears off, the whole plane shears off. Distortion of lattice in form of spiral lamp. Okay, Burgers vector is parallel to the dislocation line here, over here. All right, H dislocation is you are adding and half plane. Screw dislocation is due to the shearing effects in a structure. So usually guys, distortion doesn't happen on edge or screw. It is the combination of edge and screw dislocation. Here, this is the one. Alright. It is the combination of edge and screw is what we call as mixed dislocation. Alright. Now here, back to screw dislocation. Another one here is this screw dislocation. A screw dislocation within crystal, the atomic distortion associated with a screw dislocation is also linear and along a dislocation line AB. Here, A, B. So it moves in this direction. So it means that there is a shear force acting in this line and this line. Okay, and also this line. Alright, so it has a shearing effects, and this is your dislocation line and the Burgers vectors there. Atom position above the slip plane are designated by open circles, those below by solid circles. Right here, solid circles and also open circles. Now, as I mentioned to you earlier, dislocations happens in mix. All right, you have H dislocation over here due to the introduction of a new half plane, and also you have a screw dislocation happens here due to the shearing effects on the perfectly structured plane. Highlight that. Most crystals have components of both edge and screw dislocation. Okay. Now dislocation, since have an irregular atomic arrangement, it will appear as a dark lines when observed in an electron microscope. Highlight these. Highlight these. PEM analysis of titanium alloy. So it appears, the dislocation appears as a dark lines. Okay, all these are the dark lines. So all these are dislocation. This is also associated with grain boundaries, which I will be discussed in a later part of today's lecture. Okay, now we have covered dislocation. Now let's talk about interfacial defects or planar defects. All right, very similar to dislocation. Interfacial defects are boundaries that have two dimensions and normally separated regions of material that have different crystal structures and or crystallographic orientation. Highlight these. Interfacial defects have two boundaries, two dimension, and separated regions of material that have different crystal structures and or crystallographic orientation. Please highlight these. Now, for interfacial defects, we have three types, which is external surface, grain boundaries, and also twin boundaries. All right. So some of them, when you talk about imperfection in solids, for example, twin boundaries, it gives an extra enhanced performance in terms of mechanical properties. It strengthens the material when you have twin boundaries on it. Some goes to grain boundaries as well. It reduces the propagation of cracks if you have a lots of grain boundaries. Okay. Now, external surface, the boundaries along which the crystal structure terminates. All right. The boundaries along which the crystal structure terminates here. And normally, surface atoms are not bounded to a maximum number of nearest neighbor, so it terminates. The atoms are in higher energy state than the atom at the interior position. Free surface is also a defect. Okay, we call that as a defect, bonded to atoms on only one side and hence has a higher state of energy, highly reactive. Nanomaterials have smaller cluster of atoms and hence that are highly reactive. At all possible surface tend to be minimum. All right, if you look at grain boundaries, okay, these are the grain boundaries between different types of planes. The boundary separating two grain or crystals having different crystallographic orientation in polycrystalline material. For example, this is your plane, and then you have different crystallographic orientation. For example, this is the orientation, this direction, angle, and suddenly you have orientation in this form. So can you see a mismatch? So this is your angle of misalignment, which call that as a small angle grain boundary. If the angle of misalignment is huge, for example in this, and then you have this is your angle of misalignment, we call that as high angle grain boundary along this line. And this is the 3D view of the grain boundaries. Actually, this helps to limit the propagation of cracks. Let's see, there's a cracks happening here. It cracks, it cracks, it cracks, and then it won't crack. So this grain boundary stop the crack propagation, which in turn increase the mechanical properties of a material. All right. This is due to the simultaneous grooving of crystal meetings into each other due to the different temperature and so on. All right. Width is usually in a nominal of 2 to 5 atomic diameters, grain boundaries. Within boundary region, there is some atomic mismatch. Some atoms in grain boundaries have higher energy. That's the reason why you have boundaries. Rapid diffusion of atoms due to the lower atomic packing. This is due to it. Restrict plastic flow and prevent dislocation movement. Highlight this. These are the properties of grain boundaries. Now for twin boundaries, it is the grain boundary which there is a specific mirror lattice symmetry, which is mirror lattice. Highlight this. Twin boundary is mirror lattice. The atom on one side of the boundaries are located in the mirror image position of the atom on the other side. So this is the mirror image of this. This is a mirror image of this. This is a mirror image of this. All right. This form during plastic deformation recrystallization. Okay, only form during plastic deformation and recrystallization. That is the reason why, if you study at the performance of mechanical properties in tensile strength, if you look at the tensile stress curve, before breaking or before necking in a tensile stress, you will have some increase in stress due to the plastic deformation. And this causes the twin boundary to form in the material. Right? It strengthens the metal. Like this. Okay, guys. So that is on twin boundaries, grain boundaries, and all the imperfection. I've covered point defects. I've covered impurities in solids. I've covered dislocation and also interfacial defects. All right. And for point defects, these are the types of point defects you should know. We have 1, 2, 3, 4, which is vacancies, self-interstitial atoms, interstitial impurities atoms, and substitutional atoms. And these are the vacancy, and this is the formula. And self-interstitial atoms, you have two types, which is interstitial impurity and self-interstitial. For self-interstitial, the same atom will fill in the voids. For interstitial impurities, different types of atom will fill in the void, and that will create a distortion. And solid solution, you have two types, substitutional and interstitial. Substitutional is where a foreign material will substitute the bulk atom. Interstitial impurity, where a foreign material will fill in the voids of the bulk material, which is much more smaller. And all these can happen for this condition, under this condition. Atomic size factor, crystal structures, electronegativity, and valences. Okay. And then for dislocation, you have this, right? Dislocation, the keyword are line defects. Okay, you have H dislocation, screw dislocation, and the combination of H and screw, which is mixed dislocation. H dislocation is half plane, introduce half plane. Screw dislocation is due to the shearing force on the surface, and mixed dislocation is a mix of two. Usually all the materials have mixed dislocations. Interfacial defects, you have external surface which has under grain boundaries and twin boundaries. These are the grain boundaries because having different crystallographic orientation, and twin boundaries formed during plastic deformation and recrystallization. Okay guys, do you have any question? Do you have any question? Are you clear? All right. Okay, if there's no any question, I hope that you understand clearly and soundly of my presentation, because this is very important. Okay, I'll be conducting the whole semester using online, so I'm trying to be as detailed as possible to you so that I can help you guys to understand better in these challenging times. Okay, if you don't understand, please ask any question. All right. And for this Friday, we have class on this Friday, which is at 10:30 to 11:30. So I'll be continuing with the specification of composition and with some examples on this coming Friday. Okay. All right, let's see the questions. So the recorded video will be uploaded to Weibull. Yes, the recorded video will be uploaded to Weibull. Yes. Hammurabi rule govern both substitutional and interstitial. Yes, both, for both. Okay, Teo Tianzan for both. And for Lua Wenzheng, yes, the video, the recorded video will be uploaded to Weibull. You can share with your friends, and hope that you gain some knowledge from today's class. All right, guys, any questions? Okay, now for the valences, all right. Okay, for the valences, where is it? Over here? Yeah, valences. Okay, valences is under point defects. Okay, point by point, right? Valences happen when there is a missing atom in a plane. Okay, imagine of vacancy. All right, vacancy means it's empty, right? So a vacancy is formed due to the missing atom. There might be a missing atom in a crystal structure due to several reasons. All right, due to plastic deformation. It can be due to rapid cooling, or it can be due to particle bombardment, radiation, and so on. So when there is a vacancy in an where am I? In an atom, so the adjacent atoms tend to slip in, makes the propagating planar lines to be defect, distortion of the planes. So that is one of the reasons why we call that as point defects. And these are bad for the material. Okay, it can really reduce the mechanical properties of a material. Okay, all right. Oh, valences in hemirotary. All right. All right, valences in hemirotary. All right, when you look at this solid solution, repeating this again, solid solution, you have laws to follow, which is hemirotary law, which is atomic size factor, crystal structure, electronegativity, and also valences. So what hemirotary was mentioning in valences is, if you look at the example, okay, let me start with the example. All right, you have an aluminum nickel alloy system. All right, it's a mixture of two material. When a nickel acts as a host, all right, I'm repeating, when a nickel acts as a host, nickel has a lower valence, it can dissolve 5% of aluminum. Okay, and I talk nickel as host means that the weight percentage of nickel is higher than aluminum. Okay, it can dissolve 5 weight percentage of aluminum. However, when aluminum acts as a host where the weight percentage of aluminum is higher than nickel, it can only dissolve 0.0% of nickel. Having said that, valence means that other factors being equal, okay, all factors are being equal, electronegativity, atomic size factor, or crystal structure, a metal will have more tendency to dissolve another metal of higher valence than one of a lower vacancy. Okay, here nickel has lower valence than aluminum. That is the reason why it can dissolve 5%. But aluminum has higher valence than nickel, so it can only dissolve lower percentage of nickel. Okay, small can eat big. I don't understand. Okay, guys, so please look into the, all right, thanks Lim Weng King, hope that you understand that. Please look into what I have discussed with you today. And of course, apart from today's lecture, if you have any class, you can always email me. If you want to email me privately, you can always email me, then we can take up on that. All right? Must they exist in ionic solution to be in a solid solution? For metals, yes. You have composite as well. These are more towards composite structure, not necessarily actually. Okay, but one of the hosts must be in ionic form. That is where you can exchange your electrons. Okay. All right, guys. So let me see the attendance. Let me see the attendance. Where is the attendance? Okay, now we have only 48 respondents. All right, supposed to be 52 students. Some of them are not here, I guess. Okay. All right, students, I need your help. If you happen to know that some of your friends are not in this, haven't enrolled themselves in this class, which is engineering materials, ask them to enroll as soon as possible, because all these attendance are being counted for, right? So if you happen to know any of your friends are still haven't attended this class, ask them to attend as soon as possible. Okay. So as for tutorial and practical, I'll be uploading all the content very soon. Okay, and same goes to the teaching plan as well. Right? Any questions before I end the lesson today? All right, I assume that there is no question. I hope that I've given you a good presentation, and if there is question, you can always email me. So that's, thank you very much. That's on it today. Do take care, and I'll see you on this Friday then. All right, tutorial will start on week 2. Okay, tutorial will start on week 2. Okay then.